Alrighty, so here we go again. We are going to be talking about section 1.2 today, which is all about types of data. Just want to remind folks again that this is a supplement to the reading. It's not intended to replace all of it. Especially these first few sections, there's a hell of a lot of vocabulary. In fact, this one is pretty much all vocabulary, and I'm mostly just going to give examples. There's not really a whole lot of problems for me to work out here. So, with that said, let's hop in. So, there's two different types of categorization we're going to be talking about here. So, the first categorization is going to start out with two big categories, and then it's going to split one of those categories into two or smaller categories. So first, our first sort of break-off point, so we have data, and then it's going to go to qualitative and quantitative. So qualitative is going to be about things that are labels or descriptions. Basically, qualitative is going to be the stuff that we use the least because it's going to be non-math stuff. So some examples are the color of your hair, your gender, your zip code, let's see. Yeah, those are some good ones, right? Just things that are labels or ways to describe things. And it's actually really hard. This is sort of the order the book does it, if I recall correctly. Quantitative, if I was thinking, I might have started with that because that's a lot easier. It's going to be counts, measurements, and sort of as a rule of thumb, it's numbers you can do math to. Right? And that sounds a little bit weird, right? Because, of course, you can do math to numbers. But we're thinking about these as categories, right? And I put zip code here for a reason. Zip code is a number that you can't really do math to, right? Adding two zip codes, what does that give you? Nothing. Nothing meaningful. Probably not even another zip code. Definitely not a zip code that's related to the first two zip codes. Subtracting two zip codes from one another, even less likely to get you a zip code, right? Multiplying two zip codes means absolutely nothing. Guaranteed to not give you a zip code. Taking the average of zip codes, absolutely meaningless, right? So you can't do any math to it and still have it be a zip code and still have it be anything to do with what you started with, right? On the other hand, if you have something like height, right? The average height of a group of people means something, right? Number of guests at a hotel, right? If you had 5 guests at a hotel and then you added 5 more guests, that would mean you have 10 guests at a hotel, and that was a thing that you did that just made sense, right? It makes sense to add guests, right? You could have runs batted in, right? And really, that's standing in for every sports stat that you can think of. I don't really know any of those that you can't do math to. So you can find the average RBI of a team, you can, if one person's RBI is less than another person's, that means something, right? So that's another way that zip code fails. I can say that my zip code is a bigger number than my best friend's zip code, but so, right? That has no meaning within the context of zip codes. So talking about that person's RBI is higher than the other person's RBI, that means something as far as how they play the game. So quantitative is any data that you can do math to. And it's usually, as we said up here, counts and measures. Now, quantitative is the type of data that we can break into two more categories, which makes sense because here in this math class where we're talking about statistics, we like to deal with the data that we can do math to, right? Where we'll talk about some things in the next section that we can do with qualitative data, but once we leave next section, there's not really a whole lot we can do with qualitative data, except in some very specific contexts that the book is almost certainly going to get wrong, but we'll address that when we get to it. So the two types of quantitative data are continuous and discrete. Right. So, continuous, the definition is any value in an interval is meaningful, and usually this comes from measuring something. Right, for discrete, only specific values make sense, and this usually comes from counting something, right? So, it usually comes from counting because usually if you're counting something, you have the thing or you don't, right? If you tell me that you have 2.5 siblings, I would probably laugh at you, though not really. I mean, for one, because that's horribly rude, and we actually have a cultural idea of a half sibling, so maybe that was a bad example. Maybe if you tell me you have 2.7 siblings, that doesn't make sense. So, because you can't have 0.7 of a person, right? And usually when you tell me how many siblings you have, you've counted the number of siblings, and you're telling me that count, right? To bring our examples down here, right? So, examples, the number of guests in a hotel would go here. Technically, runs batted in, I think, is discrete, but we often talk about averages there. So I'm going to leave that off for now. We'll touch on that a little bit more. But height is definitely continuous, because, those quarter of an inches matter when you're, 4'11" and a quarter, as my aunt will tell you anytime it comes up. And talking about someone being, 1.795 meters tall. I don't know if that's reasonable. It probably is. It's slightly less than 6 feet, so that's probably a reasonable height. Anyway, height can be any number, right? It just comes down to how good is your tool at measuring how tall someone is, right? A lot of them can't get that specific, but some of them can, and those heights are perfectly valid heights. It's not like people shoot up by half-inch increments the entire time. So height can be any value in an interval and still make sense. whereas the number of guests at a hotel at any given moment is definitely going to be a whole number. It's definitely going to be a counting number, right? Having -3 guests doesn't make sense. Having 10.2 guests doesn't make sense. So only specific values work there. So that's the first categorization of data. We break it down into 3 categories. Actually, let me do here. It breaks down into 3 categories: qualitative, continuous quantitative, and discrete quantitative. And that's honestly the most common classification. That's kind of why I did it first. But we do have this second categorization, which has its place, and can be very important. It is fully sort of ordered, and a little bit more distinguishment between various levels, right? So the first one is called nominal, and this is, like it sounds, names or labels, right? So some examples is your favorite pizza topping would go here, or your jersey number might go here. Your actual name, of course, goes here. But anything that's just a word that labels something. And so obviously if we were matching these up, this is a type of qualitative data. Secondly, we have ordinal. So this is, again, it's a category of qualitative data. But it is qualitative data that can be ordered. And here when we say ordered, we don't mean it accepts instruction well and will follow orders. We mean that it can be put in a meaningful best to worst, top to bottom order, right? So some examples for this are grades, and by this I mean like the A through F thing, right? Those are labels. That's qualitative. It's not numbers. I can't do any math to it. But there's definitely an order there, right? A, B, C, D, F. It's clear what order it is, things like that. Rankings, obviously, it's kind of in there in the name, like if you have first place, second place, or even if you're doing something like worst, bad, okay, good, best, right? That sort of thing. That's qualitative data. There's no numbers there. We can't do math to that. You can't take the average of worst and good, at least not in a mathematical sense. You probably can in a conceptual sense, but we're talking math here. But there's also a definite order to that, right? You wouldn't say worst, best, okay, good, bad. I mean, you might, but that's kind of silly, right? There's sort of a built-in order to it. So the third one is interval. So interval data is quantitative. It also has an order, and let's see, I think 0 is not the absence of something. So this is sort of a weird one, right? So quantitative here means that you can do math to it. Specifically, the book sort of picks apart differences, right? You can subtract one from the other and it makes sense as its sort of distinguisher. But this last one is really the important one because it's what makes it different from the next category. And that is that having 0 in something doesn't mean that there's nothing there, right? So example is birth year, right? The year you were born, 0 doesn't mean that you weren't born. I mean, it means that you're almost certainly dead now, unless you're a vampire, and that's pretty cool. But 0 being your birth year doesn't mean you weren't born. The temperature, at least Fahrenheit or Celsius, 0 doesn't mean an absence of temperature. In fact, in Fahrenheit, it means pretty damn cold. And that's an important temperature to be had. So having 0 temperature, it's not really meaning the absence of what you're measuring. Let's see, what was my other one here? So I'm going to put grades down again, and then I'm going to specify what I mean. So first grade, second grade, and so forth. Right, so that's a little bit weird because that almost seems like it should be qualitative, right? Because I used a word there. Grade is not something I can do math to. But if we just call this 1, 2, 3, and so forth, then subtraction makes sense, right? If you have a third grader and a first grader, then you know that they are 2 years apart in school, right? So the difference 3 minus 1 was meaningful. It made sense. But 0 again doesn't indicate some sort of absence, right? It doesn't indicate that something's missing out of this. But when it does, in different examples, when it does, we have ratio data, which is quantitative. I just wrote it up there. You'd think that I could look a few inches up and see it. Ordered, and 0 means the absence of something. And one of the weird things that this means is that multiplication and division suddenly mean something, right? If you take the year you were born and the year someone else is born and you divide them by one another, that doesn't mean anything. If you multiply them by one another, that doesn't mean anything. But the minute you have something like price or age, then knowing that someone is 2 times as old as you, right, which is secretly getting at division, is meaningful. Knowing that someone's birth year is twice what someone else's birth year is, for one thing, that doesn't make much sense. Again, we'd have to bring vampires into the equation for that to be a reasonable thing to possibly be true. But it really doesn't tell us anything, right? If I told you that Bob's birth year was twice as much as Jim's, then you wouldn't know how old either of them were. And there'd be no way to guess. But if something is half price, right, that means something. more than the other ones do. So again, this sort of categorization is slightly less common, at least from what I've seen. When you get to your specific disciplines that might use this, you might see it more often. But it's another way we can put data into different types of boxes. And it's a lot of vocabulary, a lot to go through. The book has even more examples. I tried to pick different examples than they did, which is why some of my examples are a little bit awkward, because they chose the obvious ones, like greedy jerks or something. I don't know. But there's a lot more stuff in the book. This is all just a sort of supplement, sort of going over some thought processes, as opposed to just reading the bare words. And next time we'll be doing our last bit of descriptive, is it? It's not quite last bit. It's the last bit of serious vocabulary stuff. We'll be getting some vocabulary here and there as we go on, but this next section will be our last one, where it is almost primarily vocabulary. And so I'll see you with that one.